Curtius rearrangement is the thermal decomposition of acyl azides to isocyanate with the removal of a molecule of nitrogen. Isocyanate is an intermediate, and upon reaction with different nucleophiles, it can convert to a final stable product. In this video, we're going to talk about the mechanism of the reaction and the different expected products obtained as a result of the reaction of isocyanate with different nucleophiles. So let's begin. So Curtius rearrangement is the thermal decomposition of acyl azides to isocyanate. And this reaction or this conversion is accompanied with the removal of a molecule of nitrogen. So let's see how we can convert acyl azides to isocyanate. So this is how we can write an azide. You can see we have three nitrogens connected to each other. The terminal nitrogen has formed two bonds. It has a negative charge on it. The central nitrogen has formed four bonds, so it has a positive charge. And upon heating, it will lose a molecule of nitrogen in this way. So this negative charge is shared between these two nitrogens, and as a result, these two electrons are shifted towards this nitrogen. And as a result, we get another intermediate in which now this nitrogen has a negative charge. It has now formed two bonds, and the central nitrogen again has formed four bonds. The terminal nitrogen now has three bonds, so it is neutral. Now, at this stage, it can lose this N2 molecule, and this nitrogen that is attached to the carbonyl has a negative charge. Now, to remove a molecule of nitrogen N2, this bond has to shift towards this nitrogen because it has a positive charge, and because electrons are being shifted away from this nitrogen which has a negative charge, so it gets electron deficient, and as a result this R group is transferred towards this nitrogen. So we have a new bond formation, that is the bond between the R group and the nitrogen, and as a result this negative charge is then shifted between carbon and nitrogen, because when this R group migrates, it takes the bonded pair along with it, so the carbonyl carbon gets electron deficient, and as a result these two electrons can be shared between carbon and nitrogen. So we have a double bond between nitrogen and the carbonyl carbon, and then of course we have the oxygen double bonded to the carbon. So this is how we get the isocyanate. Now you can see that a rearrangement has taken place, and a rearrangement of this R group has taken place. So this R group gets detached from the carbonyl carbon, and its new position is the nitrogen, and this nitrogen allows the R group to get attached in the form of a nucleophile. So R group actually brings the electronic pair towards the nitrogen. So this nitrogen actually is electron deficient. So it is the rearrangement of a carbon towards an electron deficient nitrogen. So this whole rearrangement process is known as Curtius rearrangement. Now, a question arises here. You would be familiar with another term, nitrene. Nitrenes are electron deficient species in which nitrogen is bonded to one atom and it has this extra pair of electron, right? and this is what we call a nitrene. These are electron deficient species because the nitrogen has 6 electrons, 1 2 3 4, and the 2 of the bonded pair, so the octet is not complete, and that is why it is an electron deficient species. So the question arises here that whether this conversion of the acyl azide to isocyanate goes through a nitrene intermediate like this, and then there is rearrangement or shifting of this R group towards the nitrogen like this, and it is converted to isocyanate, or it is a concerted process and this azide is directly converted to isocyanate. So experiments have shown that this thermal decomposition of acyl azide to isocyanate is a concerted process, which means that this nitrene is not formed while azides are converted to isocyanate. So this conversion of azide to isocyanate is a concerted process. So all the bond breaking and bond formation takes place in one step and it doesn't go through this nitrene intermediate. However, if the reaction is carried out under photochemical conditions, like if you allow this azide to convert to isocyanate in the presence of light, then this azide first converts into a nitrene intermediate, and in the second step this R group migrates towards the nitrogen in the same fashion as shown above, and we get this isocyanate intermediate. So the difference between thermal and photochemical reaction in this rearrangement is that under thermal conditions, this rearrangement is a concerted process and no nitrene intermediate is involved, while under photochemical conditions, you may get this nitrene intermediate and then it will be converted to isocyanate. Now, the experimental evidence for these two different types of reactions is that when the reaction is carried out under thermal conditions, there is no evidence of the formation of side products that actually originate or proceed from the nitrene intermediate. Like these nitrene intermediates can form different products, they can undergo insertion reactions or other types of reactions. So those types of side products are not observed here, but under photochemical conditions you might see products originating from the insertion reaction of nitrene, for example, and that is an evidence that photochemical conversion of the azide to isocyanate goes through the nitrene intermediate, but under thermal conditions the reaction is concerted. So this is actually the rearrangement process happening. Now, as I told you earlier that this isocyanate is not a stable product, it's an intermediate again, and it can be attacked by different nucleophiles to get different types of products. So let's see how isocyanates can react with different nucleophiles and what products would be obtained as a result. So if this isocyanate is allowed to react with water, or it is hydrolyzed in the presence of water, so you can see here that we have a carbon-oxygen double bond. So this carbon is actually between the two electron withdrawing groups. It's highly electron deficient, and this oxygen of the water will attack this carbonyl carbon, and as a result, electrons will be shifted towards oxygen, and we will have this and double bond C O OH2, plus. When this oxyanion collapses back, it allows the shifting of these pi electrons towards nitrogen, which will then take a proton from this OH2. So this will become NH, and this will become a carboxylic acid moiety. And this can then lose a molecule of carbon dioxide to form amines as the final product, right? So if isocyanates are hydrolyzed with water, amine is the final product that is obtained. What if we react these isocyanates with alcohols? So again, the same oxygen of the alcohol will attack the carbonyl carbon here and shifting electron towards this oxygen. And in the same way, we will have this oxyanion. And in this case, we will have RH plus. And when it collapses back, it will shift the electrons towards nitrogen, which will abstract this proton. And as a result, we will have the formation of a carbamate. So when isocyanate reacts with alcohol, carbamates are formed. This isocyanate can also be made to react with amines. So if it reacts with RNH2, for example, again the lone pair on nitrogen will attack the carbon here, and we will have the formation of this intermediate, which again will collapse back, taking this proton, and as a result we will have RNH, then carbonyl, and then NHR. And you can see here that it looks like urea, but it's not absolutely urea. We have R groups attached here, so this is actually a derivative of urea. So when amines react with isocyanates, urea derivatives are produced. So these are the different reactions of isocyanates with different nucleophiles, leading to different types of products. So this is all about Curtius rearrangement. We will come up with more named organic reactions in the upcoming videos. Stay tuned. Thank you so much for now.